Welcome to Blue Pen Land here. Okay, a solid sphere. This is a pendulum, right? Okay. The Q factor for this system is 200, and the period of oscillation is approximately zero point 0.4 seconds. So T is an important calculation here. Is that T is 0.40 seconds. Actually, they only give one sig fig, right? So therefore, the frequency is 1 over T. That will become useful. So do that calculation. Okay. Let's see. The sphere is displaced, so the system oscillates. Discuss with reference to the Q factor the subsequent motion of the pendulum. Okay. So the Q factor is 200, right? So what you need to do is ascertain what does that mean, right? Q is 200. Does that mean that it's heavily damped or lightly damped, right? Okay. And then just talk about how it would move. Okay. Remember, Q is about roughly how many times it's going to oscillate before it stops. Okay, so just talk about that. I think you got it, right? So first say whether that means heavily damped or lightly damped, and then just talk about the motion. Okay, the support point P, right? So we're going to shake this thing back and forth, basically, right? Of the pendulum is now made to oscillate horizontally with some frequency, right? Describe the amplitude and phase of A relative to P when, okay? So, and what's funny is in the mark scheme, they don't really talk about the phase, but I feel like we need to talk about the amplitude and the phase, okay? Remember that when it is at, if the driving frequency is the resonant frequency, right? That the amplitude is large, is high, and that the oscillator itself is 90 degrees behind, right? Oops, that's D, that's the driving frequency, that's the resonant frequency, right? When the driving frequency is bigger than the resonant frequency, right? Then let's see, the driving frequency is bigger than this guy is a slow oscillator, so we're 180 degrees behind. And when the driving frequency is less than this, then now we're a fast oscillator, so we are in phase. So decide, look at this, look at these frequencies, decide, are they the same as our resonant frequency? Is it bigger, is it smaller, right? That's what they're looking for. Now for both of these ones where it's not equal to the resonant frequency, the amplitude is small. So that's a small amplitude, that's a small amplitude. Okay, anyway, yeah.